Hi everybody, and welcome to our November webinar, where we're delighted to welcome 3D at Depth here to talk about their world-leading LiDAR technology. My name is Joseph Suter, and I'm a graduate engineer at Amenco and a member of the SUT Plus committee. So before we start, I'm just going to go through a quick introduction to the SUT and the SUT Plus. So the SUT is a multidisciplinary society for sharing knowledge between individuals and industries working within all aspects of underwater technology. So that could include underwater renewable energy, underwater electronics, ROVs, AUVs and robotics, diving, marine science, oceanography, and lots of other applications. So the SUT Plus is the young professionals subset of the Society for Underwater Technology, and SUT Plus is created by developing professionals for other developing professionals, graduates and students. And what we aim to do is increase the understanding of underwater technology within our members through a range of events that we organise throughout the year. And these events are to assist with knowledge sharing, networking, and providing industry-related skills and experience outside of the traditional office environment. Some of the events that we offer include site visits, webinars, and career support sessions. So our aim is to increase newcomers' appeal and understanding of underwater technology and related markets, and we provide a platform to develop valuable industry knowledge outside the traditional office environment. So if you're interested in joining the SUT or the SUT Plus, do look at our social media channels on LinkedIn, YouTube, and feel free to email us to inquire about membership. It's a fantastic opportunity to benefit from a range of events and discounts on publications, training courses, and lots of other benefits to joining. So I would encourage you to check us out online. So before we start the presentation, I would just say make sure that your microphone's muted. Please don't share any video, and if you've got questions, please post them in the Q&A function, and I will go through these questions at the end, and Ian will be able to answer them. So I'll hand you over now to Ian Ellis for what's going to be a fascinating presentation.
Thank you, Joseph, and thanks to the SUT for this opportunity to present our technology. So, my name is Ian Ellis. I am the Global Service Manager for 3D at Depth, and my responsibilities are to deliver our services to multiple sectors globally and to ensure that we meet our quality standards. We are a subsea LiDAR manufacturer and operator, and we provide our services globally. And really, we are providing measurements and data solutions for underwater measurement applications. As you probably know, underwater measurement is critical in a variety of settings for your offshore assets, submerged environments. It's technically complex, it can take time, it's extremely costly, and it's potentially hazardous. So it's vital that we extract the maximum possible value from the data that we can gather in water. There are a variety of obstacles to measurement in water, but by finding a way to turn data into insight, underwater measurement offers us a chance to reduce risk, manage costs, comply with legislation, and drive forward efficiency. And to do that, we are introducing our company. We are experts in underwater LiDAR measurement. We are the world's only truly commercial LiDAR technology company. And we offer a portfolio of measurements for inspection, survey, diagnosis, and monitoring. And our end-to-end approach goes beyond simply taking the measurements, and we can work with you to get to the answers that you need for your projects. Digital products and services are built around our patented LiDAR acquisition technology. This is pulsed laser light. We are able to deploy the sensor and measure over an extended range to maximize efficiency with minimal disruption to the marine environment, and even at the most challenging depths and in the most hostile. Our standard sensor is 3,000 meter rated. How do we compare to some of the other in-water measurement technologies? We have an extended range, higher resolution. We're not affected by low light or optical distortion. And we believe that this gives us an extended range and thereby an increased efficiency. So the idea is that we measure assets and environments in 3 dimensions, and then over time, when we return to them, we can assess change over time. The output is high quality, millimetric point clouds, and with these we can inform a variety of marine activities, exploratory surveys, structural monitoring, diagnosis of damage or change. Use the point clouds to measure between any point to any other point. We can model geometric shapes and some other use cases. The idea is that we reduce operational costs, reduce carbon footprints by delivering data in less time to have a positive impact on a project budget. A cost-effective 10-meter single pass eliminates the need for runs and additional heights, significantly reducing carbon emissions at sea. We can measure in any water, so that is in the nuclear industry. And we're used to measure the gaps between infrastructure and to check its integrity. Offshore oil and gas, the renewable sector and offshore wind. We can look at subsea pipelines and cables. We've been involved in underwater research, in coral mapping, archaeology, and increasingly we're used for utilities and hydroelectric dams. So our LiDAR can work in any water environment. The principles of our technology, so LiDAR stands for light detection and ranging. We pulse light at 40 kilohertz, 40,000 times a second, and we have precise timing to know when the pulse has been emitted. The light travels in waves, which is known as propagation. There is a reflection from the target or the environment. That reflection of the pulse is detected, and again, precise timing is recorded. Using the constant speed of light, we then have a slant range. And then knowing the orientation that we project the laser, we are able to coordinate a point. And to date, we have pulsed our laser systems in excess of 1.2 trillion times and made an awful lot of data points. So moving into our hardware and how we deploy it into the water. This is our optical canister mounted on a mechanical pan and tilt unit on a work-class ROV. We have a couple of electronics canisters. We use a conductivity, temperature and density sensor to profile the water column parameters that influence our range accuracy. And we have all the typical deck test units, mounting frames. But our operator sits at a laptop and commands and controls the sensor through internet or fiber communications channels. What it looks like, on the left, we have a diver frame with our 250-meter green umbilical, which can be deployed from a vessel crane. In the middle, we have a diver cube, which is a far smaller unit. This can be handled by divers inside manifolds or interconfined spaces using airbags. And then on the right, we have probably our most common deployment currently, which is to mount to the buoyancy level of an ROV. And then you can see the pan and tilt motor has the sensor to starboard, and it will be commanded to rotate and tilt through a number of positions to increase the field of view. We have a couple of ways of scanning with the sensor. The first is what we call static LiDAR. This is typically an ROV commanded to sit in a stable position on the seabed. The ROV is essentially a tripod for our scanning system. It provides a stable platform when it embeds. There is no motion correction required for this application, and the data collection is relative to the optical reference point of the optical canister. the emission point of the laser, if you like. This allows us to have a high density of points, and we can perform multiple collections from one position, which can facilitate multiple measurements. At the bottom, you can see a typical scanning sector for a deep water field, a semicircular coverage of the laser. This animation will show roughly how the sensor operates. Vehicle comes to rest, the sensor is commanded to its first scanning position, the laser line then moves through the scanning sector. The sensor is then commanded to turn or tilt. Next sector is collected, and by this method of combining 30-degree by 30-degree scanning sectors, we increase the overall coverage from a single position. The collection, which is being animated, we would term a scan position. As the laser strikes the seabed, the spools, the assets, points are returned from their reflections, and we are able to coordinate them. To ensure that we have adequate coverage and some quality control redundancy, we will scan from a second location compared to. And at the moment, with our current generation of sensor, the SL3, a vertical metrology typically takes around 3 hours or less. And with our next generation, the SL4, which will pulse 6 times faster, or 240 kilohertz, we expect our acquisition times to greatly improve. Our second collection method is termed dynamic LiDAR or motion LiDAR. This is where we mount on a moving vehicle, ROV, AUV, ASV. This is mobile and again touchless. It allows us to collect far more data because we're covering a larger area, greater speed. But additional sensors are required. This is an absolute survey method where we apply position and motion to the laser line scans and combine them together to create a point cloud, as you can see on the bottom right. So why should you consider the use of subsea LiDAR for your projects? Well, we have a fast deployment and survey time. This can provide vessel time savings, which are connected to reduction in our carbon footprint. It does not require direct access to hubs as it's non-contact. There are no metrology interfaces required. No seabed aids, depth loops are required. We can collect additional information on the seabed assets as you scan. It facilitates combination of terrestrial and subsea data sets, and thereby can be used to perform inferred metrologies or to create digital twins. The LiDAR system typically has a greater range than laser triangulation and photogrammetric systems. It's not affected by ambient light. Each pulse provides a direct measurement based on two-way travel time and is available in real time. We have some field-proven assisted and remote operations capabilities and a range of sensor deployment solutions which are designed and produced in-house. Our subsea LiDAR point clouds are visible in real time during collection, so you can be confident that we have the coverage that's required. We have proprietary noise filtering in our software, which reduces processing times. Our quality controlled results are typically available in 12 to 24 hours from acquisition. We use terrestrial software packages primarily produced by Leica Geosystems to produce our results, so you can have confidence in the software that we use. We are able to export our point clouds in a variety of industry standard formats: LAS, PTS, E50S7, STL, STEP, DXFs. These are transferable between most software packages, engineering packages, CAD packages. They are industry standard and allow us to share our information with the customers. The system is not export license controlled. It moves very quickly globally by air freight, It's a couple of pallets of equipment, which, often goes offshore on rigs, small construction vessels inside nuclear power stations, hydroelectric dams. The system does not require full gigabit Ethernet communication channels and has been installed on practically all world-class ROVs. So when we consider some of the applications for the technology, our most common project type is metrology. Many of you will be familiar with this. We are able to extract the metrics between spool piece connection points, horizontal slope and vertical ranges, seabed profiles. We don't need to touch the assets to achieve these measurements, and where there are multiple spools in the field of view, we can compute a couple of metrologies from the same scans. We are increasingly used for asset integrity checks, to inform decommissioning scopes, to assess marine growth, anode activity, assess debris or damage, settlement, subsidence, change over time. Millimetric measurements can be extracted from the point cloud for any engineering requirement. This allows for in-depth investigation without the need to recover assets to the surface, and informs actions for corrective steps. Pipeline inspections and analysis. The point cloud can again be used. The data can be moved into some of the hydrographic pipeline packages made by QPS and IVA. You can digitize the pipeline, assess free span height, deformation, change in different operating modes, assess the size of impact damage or cracks, coating damage. There are a variety of use cases, and we continue to work on new applications across industry. Point cloud can be used to create 3D mesh surfaces, assess curvature, lateral separation, distances, angles, heights, and as I've presented, we can collect this information statically or dynamically, dependent on your requirements. Remote operations is obviously of interest to the industry as we look to remove personnel from the field, remove them from harm's way, and to reduce some of the environmental impact of travel, reduce operational cost. Our business with the development of its SO4 system has established workflows and training in place. Our systems are field proven, and we integrate our hardware with the support of the ROV teams offshore, typically. When we began to investigate this, we felt it was important to talk about the different types of operating mode we have. So for us, standard operating is 2 people offshore with 24-hour coverage, with additional support from onshore as required if the pace of collection is quick. Assisted operation is where we put 1 person offshore and then with communications links support them from shore. But clearly our operator can only work 12 hours a day, and we will need our customers to provide a point of contact for the opposite shift. Remote operations for us is where we provide no one offshore, and the client will supply points of contact who are trained and competent in the use of our equipment. All of the collection will be managed from onshore, and all of the processing will also be conducted onshore. Our business began its path towards remote operations in 2019, when our low bandwidth command and control interface was developed for our autonomous vehicle called the Saab Sabertooth. Our offshore testing simulated low bandwidth at 6 kilobits. And in 2020, when COVID hit our industry, the demand for single operator collection offshore increased, and adapted this command and control interface for remote operations. We're working on the compression and transmission of data. In 2021, the 3D at Depth performed its first fully remote metrology in Australia. None of our personnel were in the country. The equipment was sent by air freight to our customer, and their personnel coordinated the interfacing, while onshore from the USA and France, we operated the system remotely. This mode of working remotely requires a transfer of competence land to offshore. Someone has to do some of these tasks. So we have to train our customers' personnel. We have to have the ability to support them remotely to succeed. And remote operations introduces some new risks which must be mitigated. This training and support has a cost, and we have to agree on who pays for this to achieve the benefits of remote operation. So we began some years ago to prepare for this training. We have a facility in Norwich in the United Kingdom, where my colleague James, who you can see on the screen, is able to use a combination of video switching webcams to provide an in-person experience remotely. Our customers' personnel join a Teams call, much like this, and James steps through the physical installation of the equipment, its operation, and the health and safety considerations. And we ensure that our customers' personnel are comfortable to take on the task, so that when we come offshore, there's no project impact. Modern communication systems in recent years have facilitated this remote capability, and there are a variety of vendors who provide a link for us to stream video, navigation displays, two-way audio communication. We basically need the same audio-video inputs onshore that we currently receive offshore. We need to be able to interact with the ROV and the vessel team to ensure that operations are coordinated. We need to see where the vehicle is positioned on the navigation display, and often video feeds can help our orientation. We introduced a compressed data format called CREAT, so that's compressed range, intensity, angle, and time, which reduces the volume of data that we have to send, and we make use of cloud computing with Azure to create our links to the offshore installation. Again, going back to our track record, this has been proven in 2021. We provided the training remotely. The equipment was sent without our personnel entering the country. We worked with them during the mobilization and demobilization, and our metrology results were delivered in 12 hours. And we believe in 2023 that we will execute additional remote operations. Move through that quite quick, and I'm hoping that there's going to be a few questions at the end of that. But we can host a number of these presentations for anyone that has an interest in 3D depth and our LiDAR technology. We own a Saab saber-tooth vehicle, which we are developing into the Kuhei Deep, which is our HAUV concept. There are many more applications across industry. You may be interested in our science and research or archaeology. We're happy to host additional sessions or to present in person as required. So with that, I'll hand back to Joseph, and we'll see if anyone wants to ask me about LiDAR.
Thanks very much, Ian. That was absolutely fascinating, brilliant stuff. We've actually got quite a few questions coming.